Hello, everyone. What Eric forgot to tell you that I'm going to speak in French as well.
Oh, no.
Well, in my defense, that's an actually joke. I admit that my French knowledge is not that good. Hopefully, I got a chance to practice with some friends here. Welcome, everyone, both of you joining us in person and virtually. Today we're going to talk, well, the title is mainly emphasizes the Vault agent. When I started thinking about this talk, the Vault Secrets operator was not actually released. Meanwhile, when I saw that it was released, so I decided to include it in this talk. So this talk is not limited to the Vault agent. However, we will explore the approaches we are able to integrate Kubernetes and Vault as an overall. A few words about myself. I am Elif. I'm a HashiCorp ambassador in Romania. Also very happy to be able to build up the HashiCorp community in Romania alongside other two amazing organizers. Trying to also write as much as possible in order to pass on knowledge, and I invite you to take a look at the blog. As a quick overview, let's start with a question. How many of you are using Kubernetes? Okay, a great deal, actually. How many of you have encountered issues when using Kubernetes secrets? Quite some. Okay. Well, it comes as no surprise that Kubernetes adoption has been quite interesting over the past years due to the adoption of microservices, also taking into account that organizations have acknowledged the benefits of using containers and containerized applications. However, as many of you may already know, Kubernetes secrets have certain limitations. And despite of these limitations, what are we able to address these? This is the time when Vault comes into action, and we'll see how HashiCorp Vault is able to address these limitations and improve and make our systems more secure. Afterwards, we'll deep dive into the manner in which we are able to integrate Vault and Kubernetes, also doing some hands-on time showcasing these approaches, and of course, draw some conclusions together. Well, a lot of workloads are currently sitting on top of Kubernetes. There are a considerable amount of studies. An example would be the Gartner's 2022 Hype DevOps report for Agile, in which it is known that Kubernetes adoption will continue to increase over the next years as well. This comes as no surprise because, as I was saying before, it is indeed beneficial to development teams and also DevOps because readiness and time to production has gone much lower. On the other side, there are other reports showing that security concerns in the Kubernetes ecosystems are, let's say, an interesting point, because in a recent study from Red Hat, the DevOps report from 2023 shows that a lot of professionals are concerned about the amount of money invested in towards security. It is a 7% raise in comparison to the previous year. Thank you. Well, that being considered, we are still witnessing a steady growth of Kubernetes as efficiency has increased over time. Well, Kubernetes secrets are actually not a secret. Kubernetes secrets are stored unencrypted in etcd. This is the key value data store of Kubernetes. We have some, let's say, major disadvantages of using these. There are few encryption options, despite the fact that there are some identity providers able to help with encrypting the data at rest. This is not sufficient because this approach might not meet certain security requirements of the companies we work with. Moreover, configuring such providers requires certain actions to be taken by the cluster administrator. So it is not actually an easy task. Limited access control. we are not actually able to track down who accessed certain data or when this data has been accessed. Moreover, in case a person gets access to the cluster, it is rather easy to get access to all the data stored within that cluster. So security breaches are rather easy to encounter. Limited key rotation. Well, natively, Kubernetes secrets are not meant to be key rotated. Moreover, a great disadvantage or drawback of such an approach is the fact that we need to restart all the pods using such secret, which results in a service outage. And this is, of course, not desirable. Limited audit trail. Well, this is self-explanatory. Who accessed the data and when, and how, let's say, these actions are actually recorded, which is not possible in case of using old plain Kubernetes secrets. Taking all these and coming back to Vault, why actually choosing such a tool? Well, there are a lot of advantages. However, before that, what is Vault? Vault is a platform obviously developed by HashiCorp, which is aimed to help us in developing, in storing and managing sensitive data such as passwords, API keys, certificates, and nonetheless Kubernetes secrets. Vault provides a centralized secrets management. This means that every secret or data are stored within a single place. This reduces the likelihood of teams managing secrets independently or having these stored in several places. Fine-grained access control. Vault comes natively with fine-grained access control mechanisms, which allow us to set privileges for certain data, either per application basis, per teams, or per individual. Besides or additionally to the, let's say, plain old static secrets, Vault is also able to help us with the use of dynamic secrets. Due to the limited livelihood of these secrets, the security breaches are less likely to happen. Encryption. Well, data is encrypted natively during transit and at rest, which comes in addition to only securing or encrypting etcd at rest. So Vault comes additionally helping us to encrypt data in transit. And of course, audit logging. We are able and we know at every point and single point of time who did or accessed certain data. I actually quite like this diagram because it showcases the efforts HashiCorp has put over the years in order to align Vault with the industry trends. As microservices adoption has increased over the year, we are able to see how Vault has evolved in order to support these movements. As an example, in 2017, with the release of Vault version 0.8.3, we see the release of the Kubernetes authentication method. Afterwards, the Vault Helm charts for the community version, also for the enterprise one, have been released. And in our case, the attention will be drawn over the CSI driver, Container Storage Interface driver, released in 2021. The Kubernetes Secrets Engine in 2022, the Vault Agent Sidecar Injector, and very recently, the Vault Secrets Operator. And I think I need to update this diagram because it has just become generally available. The first one, well, I thought it would be the best approach to take them in a, let's say, chronological order, would be the container storage interface. In a nutshell, the container storage interface allows pods in Kubernetes to consume storage backed up by Vault. This means that using Kubernetes native resources such as persistent volumes and persistent volume claims, we are able to consume data from Vault. Despite the fact that it is not recommended, we could sync these secrets from Vault naturally as Kubernetes secret. However, this behavior is not desirable because in the end, the data from Vault will end up being stored in etcd. The pods using the CSI driver are able to consume secrets by reading those from a certain path in the files in the pod's file system. The Vault Agent Sidecar Injector. This is a mutating admission webhook controller that alters the pod template definition and automatically injects secrets into pods. A mutating admission webhook controller has several steps. In a nutshell, despite the fact that the pod or the deployment, let's say easier, a pod started with a single container, due to this mutating webhook controller, the pod definition is changed. This means that there is a Vault agent init container introduced, which, as you might know, an init container runs before every other container in the containers list. And there is additionally a Vault agent sidecar container, which runs along the main one. It is important to notice the sidecar pattern, which is the main key point of the injector, because we apply the principle of separation of concern. Our application doesn't need to be aware of Vault, because the other containers are taking care of the application to have the necessary data in order to properly function. This also applies to the CSI driver. So in case previously the easiest approach or the handiest approach was for an application to simply integrate with the Vault API, as applications and architectures have evolved and the effort to alter the code base of applications was great and very costly, we needed different approaches so that we simply inject the data and applications do not have any Vault knowledge. The third approach, and I think the newest and the nicest, and I'm going to argue why, is the Vault Secrets Operator. The Vault Agent Sidecar Injector has a small disadvantage. Well, I would say disadvantage because there is no good tool that is just the right tool for the right job. The disadvantage of the previous approach is that the Vault Agent Sidecar Injector gets deployed as a daemon set. A daemon set is a Kubernetes resource that ensures us that there is a copy of the same pod running on every node in our cluster. However, this means that we need to allocate more resources in order to have the injector up and running and properly intercepting events in our cluster. Moreover, having an init container and a sidecar container, as mentioned very early this morning, also requires more resources in order for the whole, let's say, the whole system to work well. In contrast to this, the Vault Secret Operator comes as a deployment with custom resources, which simply watch for resources in the configured namespaces that ask for certain set of data. We'll see very soon in the demonstration side that the Vault Secret Operator is deployed using the Helm chart. It is configured to authenticate with Vault and well, I need to check the change log with the latest release, but I would say that only the Kubernetes authentication method was able, and the pod in the app namespace is able to read the data using a static secret. Very soon in the demonstration, you'll see that I have pre-configured the Kubernetes authentication method, which allows a service account within a namespace to authenticate to Vault using its token. This token gets automatically mounted at the pod. However, I need to point out a particularity starting with Kubernetes version 1.26 that whenever creating a service account, a token associated with this one is no longer created. This means that we actually need to create the token and it gets then associated with the service account. So pay attention when working with the latest versions of Kubernetes. In a nutshell, this would be the Kubernetes authentication method. Well, let's get to the fun side of it. Would you help me with the first demo, please? I have enabled very quickly the KV version 2 Kubernetes KV v2 secrets engine and written a, let's say, dummy secret. I have installed Vault using the official Helm chart, and you'll see in the first example that CSI, container storage interface, is enabled in the Helm chart. I hope you are able to see well. Also, I have installed the secret store CSI driver, and the Helm chart was not very, let's say, not very customized. The first, could you pause a bit, please? Thank you. The secrets provider class works with the secret store CSI driver, works with a custom resource called secret provider class. That is configured with certain parameters in order to read secrets from Vault, and then we'll see how the deployment is configured in order to use it. Could you go further? Thanks. Let's check that the secret provider class exists in the namespace, and it does. Let's pause a bit here for a second. Okay, this is a rather simple deployment which uses the Nginx container. Let's go a bit further. Okay, and you see the fact that everything is mounted as a volume, and that volume is backed up by Kubernetes. Creating that, we have created a deployment, and of course the next step is to check that everything is in place. The pod is up and running within the HashiDays namespace, and we'll soon see that the files are mounted at the given path. By default, these are read for /mnt/secret store, and I expect to see PG user and the PG password. And indeed, the first one is there, and it is developer. And the password is, well, I have destroyed that Vault instance, so don't try to hack it. Well, I do not want to give you the impression that I'm just pasting passwords. Okay, now I want to show you the following. I have deleted the deployment and the secret provider class previously created, and I want to show you how we are able to create or to sync a secret. So I'm going to document the fact that there will be a secret object created as well, which will reflect the PG user, respectively the PG password. And the secret name will be PostgreSQL minus credentials and will be a plain Kubernetes secret. So, the secret provider class is in place. However, we should have no actually secrets created in that particular namespace, and there are none. Let's alter the deployment file. We need to define an env list in which we specify the environment variables to be injected, and from the source, I mean the secret which is to be created. And you'll notice something very interesting. Despite the fact that the provider class is in place, there was no secret created. However, upon the creation of the deployment and defining the environment variables which are read from that secret, actually the secret will be created. Yep, they are in place. And indeed, the secret was created. I also, well, this is just for a demonstration purpose. I need to say that the fact that I created the secret ended up being in etcd. and it is a highly discouraged practice. Also, the documentation would say the following. However, we need to be aware that this is possible. Decoding the secret and not decrypting it, it is indeed as said by myself. Let's go on to the second one, and that being the Vault Agent Sidecar Injector demonstration. Could we pause a bit here? Thank you. As you have noticed, I have redeployed Vault, enabling the injector flag in the Helm chart values files. And in this case, the deployment looks way easier. We have certain annotations which actually trigger the injection part. And that would be agent inject. We signal the fact that we want our pod to consume secrets from Vault. We define where the path where the secret will be, and also using Consul templating capabilities, we define how the data will be injected into the file. In that case, I'm creating the connection string for a PostgreSQL database. And the role is a role of leader. As I was mentioning, I have beforehand configured the Kubernetes authentication method. The reader role allows only read capabilities at the key value secrets engine. Let's go on, please. Thanks. Okay, creating the agent is running. You should see here that there are 2 out of 2 ready containers, despite the fact that I have defined only one. And executing into that, it is important to notice we have 3 containers, Nginx one, which is expected because I have defined it in my deployment template, and the Vault agent init container and the sidecar container. So this would be the pattern upon which the Vault agent sidecar bases on. The third one and the newest approach would be the Vault secrets operator. When at the time of this demonstration it was still in beta, could you go a bit back at the slide? Uh, 2 seconds more. Perfect. Thank you. A Vault static secret is a custom resource that comes built with the Vault secrets operator. It is configured to read a secret from the mount called HashiDays. The secrets engine is of type KV version 2. The secret name is PostgreSQL, and the destination secret is also Postgre. In case the secret does not already exist within my cluster, as you are able to see at line 12, this will be created. Important to note is the refresh after, which is 10 seconds. This means that in case the secret gets updated, the Vault operator is able to refresh the secret, and then a rolling deployment will start so that our pods start using the new version of that secret. So in case up to this point there was no availability in order to make pods aware of changing the content of a secret, there is actually now. Let's go on, please. Okay, let's see what happens when creating the resource. This is created in the HashiDays namespace. And it is indeed in place, and we should also see the secret. The final step would be confirming that the contents of the secret are as expected and as written in the KV version 2 secrets engine. Again, decoding the contents. And reading this. Well, I promise that once again that the server no longer exists. And I would discourage everyone to display sensitive information. until this demonstration wraps up, let's take some conclusions. Kubernetes will continue to grow in usage because the efficiency and effectiveness of teams and applications is continuing to grow. Either using on-premises Kubernetes, which I think it's a bit more rarely, either using a managed services, teams and large organizations are migrating their workloads into a more containerized approach. The advantages of using Kubernetes are actually obvious. However, Kubernetes, and especially Kubernetes secrets, have a lot of limitations. The greatest of them being that our data is exposed in etcd, unless this is encrypted. However, encryption is difficult. This is why Vault comes with at least 3 different approaches, and I'm sure we'll witness how HashiCorp continues to support applications and workflows and systems to become more secure from the secrets management perspective. We have the CSI driver, which was released a few years ago. We have the Vault Agent Sidecar Injector, and we have the Vault Secrets Operator. Each of these has advantages and disadvantages. As I was saying, the Vault Agent Sidecar Injector is, let's say, needs more resources. However, the Vault Secrets Operator simply intercepts what happens in a Kubernetes cluster, and using the custom resources, it is able to create secrets, which in turn will be used by our pods or applications. However, the CSI driver simply doesn't natively sync these secrets as Kubernetes secrets, because the pods will read these data from files mounted at the pod's file system. So I would say that there are various approaches. There is no right tool, but it is rather important to be aware of all of these so that one is able to choose the right tool for the right job in order to resolve a certain problem. That being said, thank you, and hope you will enjoy the upcoming labs, I think, and before that the break, if I'm not mistaken.